Hello, I am Stephen Wheat. I am a Senior Director for the High Performance Computing Business Group at Quantum Cloud Technologies. Today I will be reviewing the vision and progress towards an adaptive platform for converged high-performance computing with artificial intelligence workloads. The motivation here is that HPC and AI have long come into contact, collided if you will, and existing solutions are inadequate to suitably address the needs of each workload in a consistent manner. There is the need for a software-defined environment that seamlessly supports traditional compute-oriented HPC workloads, as well as the recently emerged AI workloads. This would be one that mimics the relative similarities between driving a car and driving a large truck. Each has its needs and specific hardware infrastructure, but the interfaces and control mechanisms can be seamlessly similar. As you know, high-performance computing, or HPC, applies substantial computing power through parallel processing techniques to solve complex computational problems and performing research activities through computer modeling, simulation, and analysis. Machine learning, ML, or deep learning, DL, and even artificial intelligence, AI, all use algorithms and techniques that iteratively learn from data to allow computers to find hidden insights without being explicitly programmed where to look. In fact, fast-growing data sets and increasingly affordable large-scale computing power are driving the convergence of HPC and AI. Let's take a closer look at the technology tools and the challenging workloads. Traditionally, HPC needs, data analytics, and machine learning needs have been supported by distinct communities developing different scientific and technological approaches due to the need to target different application domains. Today, the trend is that the need to support each, HPC, data analytics, and machine learning, is increasing, leading to the need for a converged solution architecture. A converged platform delivers the computational performance and throughput to train deep learning models, ingest and process real-time data streams, and scale resource-intensive AI workloads. In many converged workflows, AI and high-performance data analytics also allow for creating and refining more powerful HPC models. To make this converged solution real, it needs a robust platform which is inclusive of different technologies such as CPUs, GPUs, FPGAs, and ASICs, and a consistent architecture with a unified software stack to manage the computational, storage, and networking resources. In order to design a best fit platform for converged workloads, we need to understand the characteristics of real-world applications found in different domains. For example, key EDA applications rely on a parallel file system with high file throughput and a computational system with powerful double precision computing. By contrast, deep learning needs single precision or even half precision computational system assets. As depicted in the table, each application domain has its own characteristics or attributes based on a mixture of compute, memory, network, and storage needs. And storage can be with IOPS and/or bandwidth. After understanding the workload profile, we should discern how each technology fits the specific workloads. A CPU has the most flexibility for general purpose workloads. An ASIC is optimized for specific workloads. A GPU performs well for HPC and deep learning workloads. And an FPGA has the balance of cost, efficiency, and flexibility for some of each of the workloads. It is important to note that there is no single technology that can fulfill all requests and preferences in a cost-effective manner for all workloads. As with the myriad computational workload performance metrics, storage subsystems have different metrics for performance, capacity, and persistence. Understanding the data profile and workload demands leads to the best fit storage type and technology. A file system would cost more for the structured hot and cold data storage, but provides an easier way for user access. A block storage system performs the best but with limited scale, and it usually needs non-volatile memory modules to support high performance. Object storage is the cost-effective way for unstructured cold data storage with high scalability. As for the network, there are also different metrics and technologies to support different demands. The very common fat tree topology is widely employed in clusters to support high bandwidth and low latency inter-process communication. A multidimensional torus, on the other hand, optimizes for nearest neighbor traffic for such inter-process communication. And finally, for large-scale deployments, a dragonfly is a fully connected topology, which is suitable for substantially large systems, those addressing perhaps even exascale sizes. Here, we see an adaptive and robust platform with a consistent architecture for converging HPC, deep learning, and AI workloads. In this platform, all nodes, including compute nodes, utility nodes, and service nodes, are connected by a dedicated Ethernet network for out-of-band management. Each node also has extra NICs to connect with specific networks for serving in-band services and accessing data. For example, CPU compute nodes for the HPC segment or GPU training nodes for deep learning rely on the high-performance interconnect fabric, such as InfiniBand, to boost the performance in computing or accessing shared files. All the compute nodes, provided for different application and job demands, access the shared data storage pools. Compute nodes utilize a parallel file system to maximally balance the communication and computation needs of these workloads. The dedicated service nodes have a software stack for providing system management and core services such as user authentication, resource and job management, system monitoring and deployment, and more. A key feature of the QCT Converged system architecture building blocks is the means to support several fabrics on even the most dense nodes, giving optimal performance for each use case. Here, we transition to the details of QCT's vision and work towards an adaptive converged platform. Today, increasingly more customers are looking for a best practices system which meets specific workload demands. To build up an integrated workload-driven system with optimized performance takes much time and many resources to develop. It takes several stages from the initial planning to the final readiness for users. These stages include demand pattern analysis, system design and architecting, system development and deployment, system tuning and performance benchmarking, as well as piloting with friendly users and then going into production. To accelerate time to value for the customer with greatest efficiency, QCT has designed a pre-validated and pre-configured system concept to shorten the journey, which is called QCT Pod. QCT Pod stands for QCT Platform on Demand. It is a concept for an on-premises workload-driven design integrated system. Within this concept, QCT will provide various solutions with best practice hardware and software integration for specific workloads. The QCT Pod system architecture includes diverse common building blocks, which gives greater flexibility and scalability to meet the many different customers' needs. It also includes management tools to simplify the development and operating processes. And with the pre-validated and pre-configured rack-level system designs, QCT Pod solutions also offer suitable power and network cabling to decrease the time to deploy the system at the customer site. As for the implementation of QCT Pod, it could either deploy in a converged or a disaggregated structure. In the converged structure, all kinds of functional building blocks like management, compute, storage, and networking will be delivered in one rack. While for the disaggregated structure, various building blocks will be separated in different racks for individual scalability and optimal power and cooling management. To best fulfill the workload requirements, it's important to understand the attributes of each building block in QCT Pod. For example, we have big memory, accelerated, and high density featured building blocks for the compute. For the storage, we have IOPS optimized, throughput optimized, and capacity optimized building blocks. According to those attributes, we can easily provide the architecture for each customer's workload demands. To be more specific, let's look at the general architecture of the QCT Pod system. We deliver QCT Pod in management, compute, and storage building blocks, and each of them is connected by the network fabric, or fabrics discussed earlier. It includes diverse technology components. From the bottom up, QCT Pod would be delivered using our best-in-class hardware systems. As for the software stacks, it includes open source software and certain pre-validated commercial software recommended by QCT. With various components and building blocks, QCT Pod has the flexibility to modify the architecture by workloads. The structure of compute and storage building blocks will be much different between workloads. Some functions may not even be necessary, depending upon the workload demands. Regardless, the management building blocks with dashboard design will always be necessary to provide a robust and easy-to-use system management and monitoring functions. In the QCT Pod system, no one can directly access the compute and storage building blocks. All control and management will be made in the management buildings block, as it is important to ensure all the system resources are well managed. For the users and developers, QCT Pod includes a user interface, development tools, and precompiled workload environments to simplify the operation and accelerate the process towards a turnkey solution. With the comprehensive development platform, developers can focus on their specific areas of expertise, leveraging the core system infrastructure for the rest. It is always a big challenge for administrators to deploy and manage a cluster with hybrid infrastructure and diverse services. With QCT Pod, administrators can deploy operating systems with configuration management via XCAT and Ansible. The modern web-based dashboards, log alerting systems, and useful administration tools such as Prometheus, Grafana, Elk Stack, and Webmin are also pre-built into the system. Additionally, behind the scenes, there are a lot of internal core services such as RMS and Kubernetes supporting the management building block. To support HPC, AI, and deep learning, QCT includes a comprehensive portfolio for the specific demands. Pause here to inspect these examples of the platform building blocks. Through our strategic partners, QCT Pod includes several storage solution options, all seamlessly integrated into the pod environment. For example, for file storage, we have BGFS, Gluster, and more. Block storage, we have Accelero and more. And object storage, NetApp, Ceph, and others. With a basic understanding on the QCT Pod concept, I'll further share our experience with the life sciences community. With a trend towards personal medicine, some hot topics like next generation sequencing, molecular dynamics, and image recognition have arisen and gained great momentum. Based on those workload demands, QCT designed the QPM solution under the QCT Pod concept for life sciences researchers, administrators, and developers. The QCT QPM design has the following attributes. For management, the management building blocks include system tools for rapid deployment and easy management. They also include additional useful pre-built tools for NGS, molecular dynamics, and deep learning applications. For compute, this is comprised of a heterogeneous computing platform comprised of GPU server or servers for deep learning and HPC GPU computing, high-density compute servers for scaled data analysis and HPC CPU computing, and large memory server or servers for the NGS sequence quality control and DNA and RNA analysis. On the storage front, we have a scale-out storage system for data lifecycle management and data protection. There is a parallel file system for hot data storage for high performance demands. as well as a scale-out network file system for cold data storage for the original data storage and analysis results. To best meet customer demands, QCT has the workload tuning know-how and works closely with technology partners. Under the comprehensive ecosystem, QCT not only delivers a powerful system, but also provides the best practices software integrated with a fine-tuned workload package to enhance the workload performance and simplify the workflow. In summary, for the life sciences segment, we will continue to focus on HPC and deep learning compute building blocks to best fit the workloads like NGS, molecular dynamics, and deep learning. As for the storage building blocks, we focus on scale-out network file systems and parallel file systems to fulfill the requirements of high throughput and scalability. Pause here to review all of the details. Historically, a given medical organization might have used entry-level hardware like laptops, PCs, or even workstations to run the job. Now, more and more users need substantial computing capacity to perform their work and to address the increasing number of required jobs. QPM is designed to meet differing demands. It could basically divide into a laboratory suite or an enterprise suite. For the laboratory suite, it delivers with the all-in-one system with cost-effective benefits. It is suitable for the customers that are not familiar with cluster computing and related software and with limited budget. For the enterprise suite, it delivers the comprehensive system with enhanced performance and capacity. It's suitable for customers with more experience with HPC AI systems and with a greater workload. Here we see the comprehensive instance for an enterprise suite. Pause here to review the details. In this talk, we reviewed the offering and benefits of our adaptive platform, QCT Pod. First, QCT Pod can deliver excellent workload performance with the flexible building blocks design and the pre-configured workload environment. Second, QCT Pod simplifies the management with the administration dashboard and speed up the deployment process with suitable power and network cabling. Third, QCT Pod could accelerate time to value for the customer with pre-validated and pre-configured QCT Pod system building blocks. QCT has various end-to-end platform solutions and services based on cutting-edge technologies for different industrial applications. As with QPM, we anticipate developing pod solutions for many of these vertical use cases. Please feel free to contact us if you have any questions or need any support. Thank you for taking the time to review QCT's exciting pod and QPM solutions. We look forward to seeing you in the marketplace and working with you to fulfill your specific needs. Again, thank you for your time. This concludes this presentation.